Lecture 26, Profiling and Scalability. We had a long look already at the subject of observation, identifying areas in the execution of our program to think we can find a potential issue. A lot of our upcoming discussion is going to be centered around the idea of CPU profiling, which is just another way of saying, well, we're going to expect that's where the problem is, and we're going to identify what the CPU is doing with all of its time. This is generally predicated on the idea that CPU time is the limiting factor. And is that true? I think realistically the answer is frequently it is the case, and a lot of the things that we try to focus on in this course are about how can we make better use of CPU time, or how can we reduce the amount of CPU time that we need, or how can we employ more power that is available to us if it's going to the GPU or something like that. But it's not the only thing that could be holding us back, and it's at least worth discussing the idea that maybe it's something else. Right, let's check that assumption. Let's consider what else it could be. While we're discussing this, this is also a good opportunity to relate to the idea of scalability. What is the maximum number of users or the maximum number of transactions that we could handle with the software that we currently have? Right. We mentioned much earlier on in the course the idea of scalability is taking our software from 1 user to 100 to 10 million. Why not more? But to scale up, we're going to have to make decisions about what to do, right? We can't just say more everything. More everything might work, that might be good, but it isn't necessarily actually a good solution to the problem that we're having, and certainly it's not the most cost efficient. To do that, we're going to need some data. We're going to need some numbers. We're going to use profiling to find out what is slow and make a decision about what to change. Even if the plan isn't really to scale up and you're not worried right now about what's our current maximum or something like that, company executives might be. Giving them an estimate of what's the maximum number of users or transactions could be is not just a hypothetical scenario. I, within the past few months, was asked by a C-level company executive whether a particular system could handle 10 times as many users. The answer is yes. That's good, and that was probably the answer that the person wanted to hear. But it wasn't just enough for me to say yes. Trust me. I needed to back that up with some numbers. I needed to be able to explain, okay, on this day we process such and such so many transactions, and we're able to do this, and we can handle this many users, and when it comes down to it, we could actually probably handle 30 times as many users without too much difficulty. If we really did a good job of distributing the users across dates, then we could potentially handle even more than that, but they wanted to know the numbers. They wanted to know the breakdown. It's not enough for me to just say, please take my word for it. So if we do identify a problem in a production system, we want to experiment with it. We want to identify, can we reproduce this problem? Can we test out if an improvement is going to work? It's not necessarily going to be that easy. Right? And if our goal is to scale the number of users, be more fast is one option, but it's not the only one. And so, as we say, don't guess, measure, and I don't always test my code, but when I do it in production. Okay, but in this case, actually, the performance that we are going to evaluate might actually be meaningfully different in production as compared to your development system, right? One of the things that we'll observe, of course, is that scalability testing is not the same thing as QA testing. QA testing, when you're trying to evaluate, does the software do the thing it's supposed to do? You're looking at, does it generate the correct output, and does it do so fast enough? Right? We don't get a timeout. We don't have any major issues. That might be sufficient for the QA testing, but that's not enough to actually see if it scales. Right? When you're running it on your local machine, your limiting factors are very likely different from what's going on the actual production server, right? You want to test on production-like machines. If you have a low-end system, the limiting factor might be, say, RAM, because you might have 16 gigabytes of RAM in your laptop, and the problem goes away when the production server has 128 gigabytes. So you might spend a lot of time worrying about RAM usage when it turns out it doesn't matter. On the other hand, it could be the other way, that you have the newest, greatest, shiniest laptop imaginable, the best one that some mega corporation will sell you, and it runs great on your machine. But production servers are not like that, because you're running in a container that's getting a fraction of the resources of the system that it runs on, and so the limiting factors there are different. So if you want to evaluate a problem on, say, your local machine, or even in a test environment, the test environment needs to resemble that of production, otherwise you'll focus potentially on the wrong things. Next idea, reality principle. So it would be a good idea to use a real, in quotation marks, workload as much as one can possibly simulate. As you can see, the QA engineer orders a beer, orders 0 beers, orders a lizard, orders -1 beers, orders cat walks on a keyboard, and quality assurance. The first real customer walks in, asks where the bathroom is, and this is completely unforeseen, and the whole system crashes. Right? We need to test using a realistic workload. Legal reasons probably prevent you from using actual customer data in your test scenarios. You're probably not allowed to just make a copy of it and save that and use it as the testing data. But anything you can do that gives a good approximation of the actual data is going to be helpful, right? One possible strategy for doing that is taking the actual customer data but anonymizing it in some way. Can you reduce the amount of information in there that is personally identifiable or otherwise problematic? And if we do that, maybe then we have a good test set that actually resembles what we're doing. If you only generate test data, the test data that you generate might not be representative of actual data. You might say, in the test data, we'll generate 1% of our customers on annual subscription, and that might be reasonable, but it might not. If in real life 10% of your customers have an annual subscription and everybody else has a monthly subscription, it maybe makes a difference in how long it takes to actually do the analysis, because we have to do much more work for the annual customers to evaluate things. So if our limited test data is not sufficient, we get kind of inaccurate test results as to how much we can scale and how much things will actually be able to handle. Again, this isn't theoretical. You can imagine a couple of scenarios that are like this. You can also imagine one that goes the other way. Your test data might be actually much larger than in production, and I've recently seen this because your tests create but don't delete entities in the test system database every time the tests are run. These are functional and integration tests, and they end up creating a customer. And if the customer is not deleted at the end of the test, and it's not, then it stays there in the database. Well, every time the tests are run using the build system, more random generated customers get put in the database, and so it just keeps going. And at that rate, the test customer database is actually larger than the real one. So you might get misleading results there. Similarly, user behavior is very hard to simulate. If you're making threads that pretend to be users with the goal of simulating concurrent usage of the system, the scripts that those threads are executing may not actually represent the way users really behaved. Right? Your test example scenario might imagine that the manager wants to run the report at the end of the month so they can do the month closing procedure, but actual users might run them every single hour. That really happened to me. The manager was using the monthly end report to keep an eye on what his team members were doing all day. How many jobs did they complete, and they were doing that by running the monthly report. Well, nobody could stop him. Right? You could say, we should have designed something in there for him to get this update so we didn't have to run the monthly report to look at the Excel sheet that was generated to figure out what his employees were doing all day. micromanaging much. But we didn't think of that, and users are clever. And then there's the volume principle, and that is more is the new more. Light workloads are fine for regression testing, making sure that bugs are fixed and stay fixed, and making sure that things work the way they're supposed to work and no accidental breaking changes were introduced. But if you want to see how your system performs under pressure, you actually need to put it under pressure, right? There's kind of no substitute for that. You can simulate pressure by limiting RAM or running something that's very CPU intensive concurrently, so that you are limiting the amount of RAM that's available for your app, or you're limiting the amount of CPU time, but it's just not the same. It's really just not the same. Well, why not? The issue isn't so much the test as it is sort of what you're not seeing, right? If I want to test the app on my laptop under CPU pressure, I can just run the app while I repeatedly convert a video lecture from one format to another just to consume CPU cycles. And that does have the effect of limited CPU time available. We can see how the app is performing when CPU time is maxed out, but it isn't a good representation of what's going on in real life. If you have 500 users concurrently, you might actually never get to 500 users running concurrently and maxing out the CPU, because other reasons get in the way. You have lock contention, or you're limited by some other factor. So it's not quite the same. You can get some data. It's not to say that this kind of test is completely useless. It's not to say you should never do it. You just have to be mindful of not over-interpreting those kinds of results. And as I've already mentioned, these kinds of tests are of great interest to both customers and C-levels who are interested in hearing what can you deliver, what is the maximum performance. When they want to know, hey, we have 10,000 users, can your system handle this many users concurrently? You need to be able to give them a convincing answer. Finally, reproducibility and regression testing. And one of the key rules of science, it's here in the slides, it's called Science Rule 1, is that results need to be reproducible, right? When you write tests, you write unit tests, and the goal of unit tests is they run every time that you build the software to verify that things still work, to verify that bugs stay dead, to make sure that some changes haven't been introduced that break expected functionality. And the same should be true when it comes to performance testing. That there should be regular recurring performance testing to verify that everything is running at the appropriate speed. You don't want to see solved performance issues coming back, and similarly you want to identify as soon as possible if a change is introduced that slows down the execution of your program. And I mean, sometimes introducing something that slows it down is not the end of the world. If the intention was to make it slower by, as I say, doing more work, because we now need to add more functionality to it, so obviously it's going to take more time, then don't panic, right? That's expected. That's what's supposed to happen. If you intentionally made it slower for security reasons, again, don't panic. That's what's supposed to happen. There's no reason why we should worry, but you want to find out about these things sooner rather than later and identify whether it was intended or reasonable or not. Okay, so let's sort of leave those testing principles behind and get on to the next part of this, which is about characterizing potential problems. As I've said, we typically assume that CPU is responsible for being a limiting factor, but that's not always true, and basing everything on that assumption might actually lead us to the wrong conclusion. As Sherlock Holmes says in A Scandal in Bohemia, it is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. And this particular portrayal of Sherlock Holmes is from I don't know if it's BBC, but it's a British Sherlock Holmes from late 80s, early 90s, and this is Jeremy Brett as Sherlock Holmes, and it's kind of a nice portrayal. It's a Victorian setting, so it's keeping in the theme of the original. Okay, so with the wisdom of Mr. Holmes in mind, we need to collect some evidence before we reach any conclusions. And at a high level, we have probably 5 potential culprits that we could look at, and they are CPU, memory, disk, network, locks. We're going to talk about them in that order, not necessarily because this is the order in which in real life you want to investigate them, these are causes for concern, areas that we should be worried about, categories rather than specific issues, and this is just the order in which I'm going to talk about them in this lecture. It's not necessarily the order in which you should evaluate them yourself. Okay. So CPU is very likely the easiest to diagnose if we just look at the CPU usage that's reported for your application. Well, if it's maxed out, it tells you about where your CPU time is going. And if we look on any system, ECE Ubuntu system or something, we can use a command like htop or task manager in Windows, and it'll tell us about where our CPU time is going. And if CPU is currently maxed out, that's a hint that something interesting or concerning is going on. That's good, it's a start, but it doesn't tell us about sort of the historical thing. Is that just right now? Because sometimes we're doing something really CPU intensive right now, but is it going to be a problem? Well, in something like a Unix-like system, if we look at top table of processes, it'll tell you something like, oh, here's the long-term average, and we can see here I got a report from a system. This is a computer that has long ago been retired, but I used to use it to donate CPU cycles for protein folding and stuff like that. I'm single-handedly saving the world with World Community Grid, let me tell you. Right, but it's the load average thing that's interesting. Those last 3 numbers are the 1, 5, and 15-minute averages of CPU load, and lower numbers mean less CPU usage and a less busy machine. If you know how to interpret these, it's straightforward, but I'll give an explanation in case it's new to you. So you can picture a single core of a CPU as if it is a lane of traffic, and you are a bridge operator, so you need to monitor how many cars are waiting to cross the bridge. If no cars are waiting, traffic is good, drivers are happy, but if there's a backup of cars, then, well, people are unhappy. And when we see something like 0 to 0.99, that means we are under capacity. 1.0 represents the capacity, and as long as we are below 1, then we're under capacity. Everybody who wants to get CPU time gets it, and there's kind of no issue. 1.00 means we are at exactly capacity, so we are maxing out the CPU. We're using it to its full potential, but nobody is waiting. Anything above 1.0 means there's some backup, there's a delay, there are processes that are waiting to get CPU time. So if we have 2.0 load, that means the bridge is full and there's an equal number of cars waiting to get on the bridge. And so visually, a little representation of that. 1.0 represents everything is completely full, but everybody is driving the speed limit. Cars are packed in as tightly as they can be, but it's not a problem because there's no delay. A load of 0.5 means we're using only half the space that is currently available, so no issue there either. Everybody is able to proceed as quickly as they would like. And then 1.7 is, the lane, the bridge is completely full, and there's a fair number of cars waiting their turn to get there. So being at or above 1.0 isn't necessarily bad. As far as we're concerned, sometimes, things happen. There's a big pileup of things to do right now, so we end up with a bit of a backlog. As long as it's temporary and it resolves itself relatively quickly, then there's kind of no issue there, right? We shouldn't worry too much about temporary, transient problem. If we're below 1, but we're getting close to it, then we know how much room or how little room we have to scale up. If it's up to 70% of the maximum, then it's probably time to investigate. Is there something we could do that would reduce the CPU load? Do we need more servers or like more capacity? Do we buy a better server? Good question. If load is above 1.0, we have consistently we have a serious problem because we have lots of things that are waiting for CPU time. So we could be executing faster, but for the fact that there's not CPU time available. So that's not great. If all things being equal, we would prefer things not to wait for CPU. So that might be important. And surely if we see that like CPU usage is something like 5, this is a red alert situation, something is horribly wrong. We have more tasks waiting than are currently executing, something is going on here, and we probably need to find an explanation as to why CPU usage is so high, and try to deal with that as best we can. Now that's of course for a single CPU. If we have a load of 3.0 on a quad-core CPU, that's fine. It's there's a traffic analogy again. If there's 4 lanes of traffic and 3 of them are being used at capacity, it's as if we're at 75% utilization. So if you look at a system that has 12 cores or something like that, and you see that usage is at 7, like don't freak out. It is per CPU core. We'll talk about memory, but we're also going to talk about disk because they kind of go together in this regard. So next on the list is memory, and one way to tell if memory is actually your limiting factor is to look at disk utilization. Why is that? If there's not enough RAM available, there will be swapping and performance goes down, and accordingly scalability is also decreased by the fact that we're spending a lot of time swapping. You can ask via various tools about how much swap is being used, but that's probably not an interesting value, right? You can see here I've got an example of memory in use and swap. This is also I think from the same machine, which to my recollection only had 8 gigs of RAM. And you can look at that and you can say, we're using a lot of swap memory. But here's the thing. This can be a little bit misleading. Memory being full in quotation marks does not necessarily mean anything bad. If the CPU is maxed out, that's a problem. It means there's stuff that wants to use the CPU and it's not able to get it because it's waiting its turn. But with memory, that's not really the case, right? The memory is being used to its maximum potential, but there's no benefit to keeping a large amount of memory open for no reason. It's the same as like don't stockpile late days for the course. You don't get any reward if you finish the course with unused late days. They're there if you need them, and use them if they help. But you again don't get a reward for having them. Things move in and out of memory as they need to. Nobody hands out medals for somehow reducing the amount of memory you used or increasing the amount of free memory, that kind of thing. It's not like CPU, right? If there's nothing for the CPU to do, it goes idle. Maybe it switches to a low power state, which is good for reducing your electricity budget. But that kind of thing doesn't really happen with RAM. Data that's just not needed right now, it hangs around in memory until there's a reason to move it is fine. Right? Freaking out about memory appearing full is kind of like getting all in a knot about how the system idle process is hammering your CPU who's using 97% or something like that. And yes, a tech journalist, John Dvorak, his name is, actually wrote an article about this, about how in Windows the system idle process was using up all his CPU and he didn't understand why, and he was very upset about it. And I'm like, well, I don't know how to tell you this, John, but it doesn't mean what you think it means. So we shouldn't get freaked out about that. So we can also ask about page faults, and page faults can be inquired about using the PS command, where you ask for the minor and major faults, which gives you the major ones, that's fetching from disk, and the minor, which is copying a page from another process. The output of this is too big even for the notes. Maybe I can do a demo of it in class. but you can certainly try it yourself. This is lifetime information, though. So if your process is very long running, the number of page faults might be very large, but that's because, there's a page fault every few minutes, and it's been running for the last week. So don't freak out, right? You could also have a lot of page faults at the beginning while data is getting loaded into the system, and then not really have any more after that. But the lifetime total was really pumped up by the fact that in the beginning there were quite many of them. So again, like don't freak out, don't read too much into that because it's process lifetime data. What you actually want to ask about is for a report on swapping. And for that, the command is vmstat5, and it gives you the swap in and swap out. These are the SI and SO columns to pay attention to. And in this case, they're all 0 in the example that I show here. That's excellent. That's what you want. It tends to indicate we're not swapping to disk, and it's not the performance limiting factor. And a little bit of swapping isn't necessarily bad, but you should be concerned if you see a lot. If we have lots of swapping, it is a problem. Here's a different example that has a much larger number of swap in and swap out elements, and we sort of might consider that concerning. So if we don't see a lot of swapping, memory is not the one that's holding us back, and we can conclude it's not a limiting factor. So let's talk about, say, the hard drive. Looking at disk might seem a little bit redundant, given if we've considered whether memory is a limiting factor, because, well, if memory is big enough, we don't need to go to disk at all for some of these things. But we can take a look to see if that is in fact our bottleneck. And to ask about that, the command for this is iostat, and the device in this question is /dev/sda, and we're going to get a report about the device, and it'll tell you, reads and writes per second, and kilobytes, and average requests, and queue sizes, and things like that. But actually, the last column is probably what we're interested in, which is the utilization. The device bandwidth in this example is barely being used. It's 1.34%, so yeah, we're not really stressing out the disk in this situation. And my recollection is that system did, at least at the time when I made this, have a magnetic hard drive, so it wasn't even particularly fast. But clearly that wasn't our problem, right? This isn't the situation that we see when we would have 100%, which would be a big concern, right? Like I would be worried if I saw 100% there. It would say, what is going on? This doesn't tell you very much about what's sort of going on. If you want to know a little bit more about it for I/O subsystems, you can use iotop, the command, but this requires root privileges on the system, which probably we don't have. And that leaves us with network. We can ask about the network usage with nload, and it gives the current, average, min, max, and total values, and in fact it will draw you a little ASCII art graph if there's something to see. And it's not much fun if nothing is really happening, but we can see a bunch of data traveling in and out. For a sufficiently good network connection, there's kind of no reason to sweat it, but we could identify that maybe network is the limiting factor here if we had a slow internet connection. It's a remote system that we are connecting to out in the field, and we're relying on a cell network or something like that. We could probably identify that we're being limited in our transfer speed by the network. You could also encounter that if you have some Internet of Things devices where the customer's Wi-Fi is bad, or they're using power line adapters. All those kinds of things could actually be interesting in terms of what's limiting network speed. And the last thing that I'll suggest is maybe our code is slow because we're waiting for locks. And that might be either because we're waiting for locks very frequently, or because we're waiting for locks for a very long time. We've already discussed in the course the idea of sort of appropriate use of locks, what is the correct scope for a lock and what should be in there, and how do we limit the scope to only what is absolutely necessary. And similarly, in a previous course, or at least in a prerequisite that you should have read up on before taking this, we would have talked about the subject of deadlock, because I want to say that deadlock is a correctness problem more so than a performance problem. in any case, whatever previous course you took that covered this, ECE 252, SE 350, MTE 241, it probably covered deadlock and how to avoid it, and lock ordering problems and that sort of thing. And if you've also learned about Helgrind from the Valorant suite, it's a good idea to identify lock ordering problems that potentially cause a deadlock. So we'll skip that and just sort of move on. So how do we find what is actually going on in terms of locking? Well, one idea is if you have unexpectedly low CPU usage and that's not explainable by I/O waiting, right? CPU usage could be low because we're waiting for incoming connections from the network, or we're waiting for data to be delivered from another service, and that sort of thing could definitely be an indication that CPU usage is low without it being a lock contention problem. But if we don't have an explanation like that, we're not sure why it's the case, then there is the distinct possibility that it is caused by waiting for locks or being blocked by locks to begin with. In fact, if we have many threads that are in a blocked state of some sort, that also is maybe an important indicator that, yeah, something is going on here and they might be blocked waiting for locks. Part of the difficulty, unlike some of the other tools that we've talked about, is there exists no magical lock trace tool that tells us about critical section locks. And the pthread library, for example, doesn't have any locks tracing in its specification. And you may have seen that on a Unix-like system, the Rust threading stuff at some level may rely on the pthread locks and pthread constructs. So yeah, that's kind of a problem because it's not there in the library and we can't just wish for it and we can't just add it. One possibility is to introduce our own tracing, recording in a log that we want to enter a critical section, and another one when we're in it, and a third entry when we leave a critical section A. That's not great. It does require us to monitor that. It does require us to do something. It requires us to use it consistently and just not make any mistakes where we forgot to comment on something. But it also doesn't draw our attention to issues where there's a problem, right? Waiting for a lock isn't necessarily bad, and sometimes if we have relatively little lock contention in this, we'll have a lot of log lines saying entering and not getting blocked, whereas the ones that we're looking for where we do get blocked are a lot harder to find in the data that we get out of the logs. I did some reading about this on perflock, and it sounds at a glance like this might do what we want, but I'm sorry to disappoint and say actually it does not. Perflock is good for finding locks in the kernel, and that's not great. It doesn't really find user space lock contention. Similarly, there exist some other tools that help us to find thread switches, but that's not quite the same. Just because the thread switched, it doesn't mean necessarily it was because it got blocked waiting for a lock, and it doesn't mean that lock contention is a big problem. It could be switched because of timer interrupt or because a higher priority thread joined the pool. It's really hard to know. Something like the Intel vTune tool claims they can find these sort of problem. However, vTune costs money. You might be willing to pony up some money for making sure that your program behaves well and executes and doesn't have lock contention problem. However, it may be CPU vendor specific, right? You may have to use Intel hardware to get the benefit that you're looking for from the Intel vTune tool. Which is, I guess, great for Intel, but maybe not so great for you if you've invested in servers that use Threadrippers or something like that. With that said, we've spent a reasonable amount of time sort of discussing the idea of the profiling tools that we could use to kind of get a fix on whether our problem is CPU based or not. But I'm going to say most profiling tools and most of our discussion are about CPU profiling because actually that's most likely what it is, right? We could focus on something else if that's in fact the nature of the problem, but for the next part of our discussion we will definitely assume that it is CPU profiling, and so that's what we are going to discuss next.